The secrets of the Milky Way aren't just written in the stars, they pulse through the very fabric of our existence. As we explore our home galaxy, we uncover the silent wonders that shaped everything we know. The secrets of the Milky Way begin with a quiet truth that has shaped the story of our species. Long before we built cities or tools or telescopes, we looked up at the night sky and saw a pale, glowing band stretching from one horizon to the other. That soft river of light became our first window into the universe. It called to us, and even though we did not have the language of science, we felt that the sky carried meaning. The Milky Way was more than a pattern of stars. It was a presence, a mystery, a silent companion above every generation that ever lived. Today we understand that this band of light is our home galaxy, viewed from the inside. We are living inside a disk of hundreds of billions of stars, and when we look outward through that disk, we see their combined glow. Yet even with modern science, the Milky Way still holds a sense of wonder. It is vast beyond comparison, filled with forces and structures that stretch across unimaginable distances. Every star, every cloud of dust, every beam of ancient starlight is part of a grand system shaped by gravity and time. This first chapter is an invitation to explore that system with clarity and curiosity. Our journey will move through the heart of the galaxy, across its spiral arms, and into regions that human eyes will never see directly. We begin with the idea that the Milky Way is not a static object. It is alive with motion. Stars orbit the center like billions of tiny clocks. Gas drifts in slow tides shaped by gravity. Dust gathers into clouds that one day collapse and create new suns. Everything is moving, changing, evolving. When we observe the Milky Way, we are not looking at a painting. We are looking at a living structure. The light from distant stars took thousands of years to reach us. In many ways, we are seeing the galaxy as it once was, not as it is right now. The starlight that forms the band across our sky carries history inside it. It holds the story of how the galaxy formed, how stars were born, and how matter moved and reshaped itself over billions of years. To understand the Milky Way, we must first understand our place within it. Our solar system sits far from the center of the galaxy, in a gentle region between major spiral arms. This location matters. It gives us a relatively stable environment, protected from the violent storms and intense radiation near the galactic core. Our distance allows life to develop without constant disruption. We are far enough to stay safe, yet close enough to be part of the great galactic dance. When you step outside on a dark night and look at the sky, you are seeing only a tiny fraction of what surrounds us. Most stars in the Milky Way are too faint or too distant to be seen with the naked eye. Entire clusters of stars lie hidden in dust. Massive clouds of gas stretch across thousands of light years, silent and invisible to human sight. Yet they are real, and they shape the galaxy as surely as the stars we can see. Science gives us the tools to uncover these hidden structures. Radio telescopes detect cold gas drifting in the spiral arms. Infrared observatories reveal newborn stars inside thick clouds of dust. High-energy detectors capture the traces of ancient explosions. Together, these instruments let us step beyond the limits of our eyes. They show us a galaxy full of activity, full of complexity, full of motion. The Milky Way is not just big, it is built on scales that challenge our ability to imagine distance. Light from one side of the galaxy takes 100,000 years to reach the other side. A beam of light could cross the entire solar system in a few hours. Yet, it would take ages to travel across the galaxy we call home. This scale reminds us that we are part of something far larger than our everyday world. As we begin this 15-chapter journey, think of the Milky Way not as a distant idea, but as a real place. It surrounds us. It shapes our sky. It shaped the atoms that make up our bodies. The iron in your blood was forged in a dying star somewhere in this galaxy. The calcium in your bones once drifted through space as cosmic dust. Every part of us carries a connection to the Milky Way. This chapter opens the door, but the true exploration lies ahead. The galaxy is full of forces we will explore in detail, from the black hole at its center to the spiral arms that circle through space. We will follow the births and deaths of stars, the movement of planets, and the flow of dark matter that holds the entire system together. For now, it is enough to pause and recognize that the Milky Way is both our origin and our frontier. It is the oldest story we know and the newest mystery we seek to understand. The invitation is simple. Look up. See the soft band of starlight. Know that you are inside a galaxy that has been shaping itself for more than 13 billion years. And know that its secrets are waiting, ready to be uncovered one chapter at a time. To understand the Milky Way, we begin with its shape. When scientists describe our galaxy, they use the term barred spiral. This means the Milky Way is not a simple pinwheel of stars. Instead, it has a long central bar made of densely packed stars. And from the ends of this bar, spiral arms sweep outward in graceful curves. These arms circle the galaxy like slow-moving waves of light. If we could step outside the galaxy and see it from above, the Milky Way would appear as a glowing disk, marked by swirling patterns of brightness and shadow. The disk of the Milky Way is wide and thin. It spans about 100,000 light-years across, yet it is only a few thousand light-years thick. Most of the stars, including our Sun, lie inside this disk. They move in long orbits around the center, shaped by both gravity and the pull of dark matter. The disk holds stars of all ages, from newborn blue giants to ancient red dwarfs that have been burning for billions of years. Along with stars, the disk contains gas, dust, and clusters of matter that form the raw material for future star formation. At the center of the Milky Way lies the galactic core. This region is crowded with stars packed far more tightly than in our part of the galaxy. The light from the core is bright and intense, but from Earth, dust clouds block most of it from view. When we use infrared telescopes, the core becomes visible as a dense golden glow. Stars there move quickly, circling the central region like planets orbiting a massive object. The motion of these stars reveals the presence of a supermassive black hole at the heart of the galaxy, a subject we will explore later. Radiating from the central bar are the spiral arms. These arms are not solid structures. Instead, they are patterns shaped by gravity and density. As gas and dust drift through them, the material becomes compressed. This compression triggers star formation. The result is that spiral arms shine brightly with young, hot stars. These stars live fast and die young, so the arms always appear fresh and bright. They are the active regions of the galaxy, the places where new suns are born. Our own solar system lies in a smaller branch called the Orion Arm. It is not one of the major arms, and that is fortunate for us. The Orion Arm is less crowded and less chaotic. Here, the density of stars is moderate. Supernova explosions are less frequent. Radiation levels are lower. This calm environment allowed life to evolve on Earth without constant catastrophic disruption. The location of our solar system is one of the hidden advantages that shape the history of our planet. Beyond the disk of the galaxy lies the stellar halo. The halo contains ancient stars that orbit far from the center. These stars drift through space like cosmic fossils. Many are older than the disk itself, and some belong to small galaxies that the Milky Way absorbed long ago. The halo also contains globular clusters, which are tight spheres of stars held together by strong gravitational bonds. These clusters are some of the oldest structures in the galaxy. They shine like lanterns at the edges of the Milky Way. Surrounding everything is an even larger component, the dark matter halo. Dark matter is invisible, yet it exerts a strong gravitational pull. Without it, the stars in the outer parts of the galaxy would fly away into space. Instead, they remain bound to the Milky Way, moving in steady orbits that reveal the presence of this unseen mass. The dark matter halo extends far beyond the visible edges of the galaxy, forming a vast envelope that holds the entire system together. The Milky Way is also home to satellite galaxies. These smaller galaxies orbit around us the same way moons orbit planets. Some, like the Large Magellanic Cloud and the Small Magellanic Cloud, are bright enough to be seen from the southern hemisphere. Others are faint, stretched, or partially torn apart by gravitational forces. These satellites are reminders that galaxies interact, collide, and merge over billions of years. The Milky Way itself grew by absorbing many smaller galaxies in the distant past. One of the more remarkable features of the Milky Way is the way it rotates. Stars closer to the center orbit faster than stars farther out, but the difference is not as large as expected from visible mass alone. This strange rotation pattern was one of the first clues that dark matter must exist. It told astronomers that the galaxy contains far more mass than we can see. The Milky Way is not only stars and gas, it is also a hidden structure of invisible matter that shapes every motion. From Earth, we can see only a slice of the galaxy. Dust within the disk blocks much of our view. To build a complete portrait, astronomers combine data from many types of telescopes. Infrared light reveals stars behind dust clouds. Radio waves show the movement of cold hydrogen gas. X-rays expose regions where high-energy events took place. When these pieces are assembled, the image becomes clear. The Milky Way is a layered system, complex and dynamic, with structures that stretch from the crowded core to the quiet outskirts of the halo. Understanding the portrait of the galaxy helps us understand ourselves. Our sun is one of hundreds of billions of stars. Our solar system is a small part of a vast disk. Yet the forces that shape the Milky Way also shaped our world. Gravity gathered the gas that created the sun. The dust from ancient stars formed the planets. The stability of our location allowed life to emerge. We are part of a pattern far larger than anything on Earth, and our story is woven into the structure of the galaxy. As we move forward, this portrait will guide us. We know where we are. We know the layout of our home in the universe. From this foundation, we can now explore the deeper forces at work. The next chapter takes us into the heart of the galaxy, where the light grows bright and the forces grow strong. There, inside the crowded core, we find one of the most powerful secrets of the Milky Way. At the center of the Milky Way lies a region unlike any other part of our galaxy. It is dense, crowded, and filled with ancient starlight. Thousands of stars move in tight orbits around an unseen point, a point that reveals itself not through light, but through gravity. This point is Sagittarius A, the supermassive black hole at the heart of the Milky Way. its presence shapes the motion of everything near it, yet it remains invisible, hidden behind the veil of space and time. Sagittarius A has the mass of about 4 million suns. All that mass is compressed into a space no larger than our solar system. The gravity in this region is intense, strong enough to bend the paths of stars and distort the flow of time. Nearby stars move at incredible speeds, some reaching thousands of miles per second. Their orbits are not random. Each one follows a precise path determined by the pull of the black hole. By studying these paths, astronomers confirm that something extremely massive and compact must sit at the center of the galaxy. The environment around Sagittarius A is crowded with matter. Gas clouds drift toward the center. As they fall inward, the gas becomes heated by friction and compression. This heating can create bursts of high-energy radiation. Most of the time, however, Sagittarius A is quiet. It is far less active than the black holes found in some distant galaxies. Long ago, it may have been brighter, fed by streams of falling gas. Today it rests in a calmer phase, though faint flares of energy still ripple outward from time to time. The stars near the center tell a dramatic story. Many are young and hot, which is surprising, because the core is not an easy place for stars to form. The pressure, heat, and tidal forces near the black hole should tear apart fragile clouds of gas. Yet clusters of young stars exist. Their presence suggests that star formation in the galactic center follows different rules compared to the quiet regions of the disk. Some scientists propose that these stars formed farther away and then migrated inward. Others suggest that extreme conditions in the core create short bursts of rapid star production. Dust and gas clouds also play a major role in shaping the core. Massive clouds orbit the center in long, looping paths. Some collide with each other, releasing shock waves that trigger star formation. Others become stretched and twisted by gravity. These clouds form a complex and ever-changing environment. Observatories using infrared and radio wavelengths reveal structures that shift over decades. This movement reminds us that the center of the galaxy is not static. It is a place of constant activity, shaped by forces that act over both short and long timescales. Closer to Sagittarius A lies a region known as the accretion zone. Here, gas spirals inward like water down a drain. The gas heats as it falls, creating a thin disk of hot material. Even though Sagittarius A is mostly quiet today, this accretion zone still emits small flashes of energy. These flashes allow scientists to study the behavior of matter under extreme conditions. They reveal how gravity warps space near the event horizon, the boundary beyond which nothing can escape. No light, no matter. No information can return once it crosses that line. The motion of stars near the center provides one of the clearest demonstrations of Einstein's theory of general relativity. The orbits of these stars do not follow perfect ellipses. Instead, they shift slowly over time. This effect, called orbital precession, matches the predictions of relativity. It shows how the curvature of space around the black hole affects the motion of stars. By measuring these subtle changes, astronomers gain insight into the nature of gravity at its strongest. The core of the Milky Way also connects to larger galactic processes. Energy from this region can shape the flow of gas across thousands of light years. In the past, outbursts from Sagittarius A may have created large bubbles of high-energy particles that rise above and below the galactic plane. These structures are known as the Fermi bubbles. They stretch for tens of thousands of light years, and their existence tells us that the center of the galaxy was once far more active than it is today. life near the core would be difficult. The density of stars increases dramatically, and the radiation levels are far higher than in our region of the galaxy. Close encounters between stars would be common. Supernova explosions would occur frequently. Gravity from the black hole would create violent tidal forces. For life, as we understand it, the core is a harsh environment. Yet as a laboratory for extreme physics, it is unmatched. Every observation of this region expands our understanding of space, time, and matter. Despite its dangers, the center of the Milky Way holds deep significance for our existence. It anchors the orbits of every star in the galaxy, including our Sun. Its gravity shaped the distribution of matter when the galaxy first formed. It influenced the growth of spiral arms. It contributed to the flows of gas that eventually created the conditions for life to emerge on Earth. Even from a distance of 26,000 light years, the heart of the galaxy affects our world. As we build a clearer picture of the galactic core, we also see the Milky Way itself more clearly. A galaxy is not simply a collection of stars. It is a system with a center, a structure, and a history. The core is where this history becomes most concentrated. It is where the forces that define the Milky Way are at their strongest. And it is where some of the deepest mysteries of the universe continue to unfold. The journey through the heart of the galaxy reveals the power and complexity of cosmic gravity. In the next chapter, we move outward from the core and explore the spiral arms, the sweeping structures that give the Milky Way its iconic shape and create the environments where new stars are born. When we picture the Milky Way, we often imagine a swirling pattern of bright bands curling out from the center. These bands are the spiral arms, the structures that give our galaxy its graceful shape. Yet, the truth is more subtle than the image suggests. Spiral arms are not solid pathways of stars. They are patterns formed by waves of density that move through the galactic disk. Like ripples on a pond, these waves shift and sweep across the galaxy, guiding the flow of gas, dust, and stars. To understand spiral arms, imagine cars on a busy highway. The cars move at different speeds, but sometimes traffic slows in certain regions, creating a dense wave. Cars enter the wave, slow down, then exit on the other side. The wave moves through the highway even though individual cars do not stay inside it for long. Spiral arms work the same way. Stars and gas move in and out of the arms, but the arms themselves are stable patterns shaped by gravity. This idea is known as the density wave theory, and it explains why spiral arms can remain visible for billions of years. The spiral arms shine brightly because they are home to young stars. As gas clouds drift into an arm, they become compressed by the higher density of the region. This compression triggers the birth of new stars. The youngest and hottest stars glow blue and bright, lighting the arms like sparkling lanes across the galaxy. These stars do not live long. Their light fades after a few million years, but the next wave of star formation arrives behind them, keeping the arms illuminated. Between the major spiral arms are quieter regions of space. These inner arm regions still contain stars and dust, but the density is lower and star formation is slower. Our solar system resides in a smaller feature called the Orion Arm, or sometimes the Orion Spur. It is not as active as the major arms, and this has been beneficial for life on Earth. The calmer environment reduces exposure to supernova explosions and intense radiation. The stability of our location helped shape the long history of biological evolution on our planet. The Milky Way has several main arms. The Scutum Centaurus arm and the Perseus arm are among the largest and most prominent. These arms stretch across vast portions of the galaxy, forming the main structure of the disk. The Sagittarius arm and the Norma arm are also major features. Each arm contains clusters of newborn stars, old red giants, glowing nebulae, and clouds of molecular gas. These structures make the arms dynamic environments where the past and future of the galaxy intersect. Within the arms, molecular clouds play a central role. These clouds are cold and dense, containing the raw materials for new stars. They drift through space like dark ships, invisible in normal light. Radio telescopes reveal their shapes and movements. Some clouds span hundreds of light years. Others are smaller, but still massive enough to form thousands of stars. When these clouds enter a spiral arm, pressure and gravity begin to reshape them. Dense regions collapse into new stars, while the surrounding gas becomes heated and sculpted by radiation. Supernova explosions also shape the spiral arms. When a massive star reaches the end of its life, it collapses and releases a burst of energy. This explosion sends shock waves through space. These waves compress nearby gas, triggering new rounds of star formation. In this way, death leads to birth. The cycle of stellar life continues, influenced by the structure of the arms and the movement of matter through them. The spiral arms also guide the movement of gas across the disk. Gas flows inward toward the center in some regions and outward in others. This circulation helps regulate the number of stars that form over time. It also influences the distribution of heavy elements, which are created in stars and spread through space when those stars die. Without the spiral arms, the Milky Way would be a far less organized system. The arms shape the rhythm of star formation and the distribution of matter across the galaxy. Our view of the spiral arms from Earth is limited by our position inside the disk. Dust clouds within the plane of the galaxy block much of our sightline. To map the arms, astronomers use radio waves that pass through dust. These observations reveal the motion of hydrogen gas as it orbits the galactic center. By measuring the speed and location of different gas clouds, scientists can reconstruct the shape of the arms. This work is ongoing, and our map of the Milky Way continues to improve. Though we cannot step outside the galaxy to see it directly, the picture becomes clearer with each decade of observation. The spiral arms tell us that the Milky Way is not static. It is a living system shaped by gravity, rotation, and the continuous birth and death of stars. As our solar system travels around the galaxy, it will eventually pass near different arms. These encounters may influence the flow of comets, the climate on Earth, and the overall environment of our solar neighborhood. The spiral pattern is not just a visual structure. It is a dynamic engine that helps drive the evolution of the galaxy. As we leave the sweeping arms and continue our journey, we move into the regions where stars begin their lives. The next chapter explores the process of star birth, the transformation of cold gas into shining light, and the forces that turn the darkness of space into the brilliance of new suns. To understand the life of the galaxy, we must begin where every star begins, inside cold and quiet clouds of gas and dust. These clouds drift through the spiral arms like dark oceans, invisible in normal light. They are made mostly of hydrogen, the simplest and most abundant element in the universe. Within these clouds lie regions of calm darkness, where temperatures fall low enough for matter to gather and settle. These regions provide the conditions for one of the most important processes in the Milky Way, the birth of stars. Star formation begins when part of a cloud becomes dense enough for gravity to take hold. Sometimes this density builds slowly as gas collects over millions of years. Other times, a shock wave from a nearby supernova triggers the collapse. When the collapse begins, the cloud contracts inward. As it does, the material heats up. Gravity pulls harder as the core becomes heavier. The collapse continues until the pressure and temperature in the center reach extreme levels. At this stage, a protostar is born, a young object that shines not with fusion, but with the heat of collapse. A protostar is surrounded by a swirling disk of gas and dust. This disk forms because the collapsing cloud rotates. Instead of falling straight into the center, material flattens into a spinning structure that circles the young star. This disk holds the ingredients for planets, moons, asteroids, and comets. Over time, the material clumps together. Small grains become rocks. Rocks become planet-sized bodies. The planets that one day orbit a mature star are shaped in these early stages, inside the warm and dusty cradle of the disk. As the protostar continues to grow, its core becomes hotter and denser. When the temperature reaches about 10 million degrees, hydrogen atoms begin to fuse into helium. This fusion releases energy. The protostar becomes a true star. The moment fusion begins marks a new chapter in the life of the object. Gravity no longer has complete control. The outward pressure from fusion balances the inward pull of gravity. The star enters a stable phase known as the main sequence. Most of the stars in the Milky Way, including our Sun, are in this stage. Star formation does not happen in isolation. It often occurs in clusters. A single cloud may give birth to hundreds or even thousands of stars. Some will be small and dim, destined to shine quietly for billions of years. Others will be massive and bright, burning through their fuel quickly. Massive stars shape their surroundings in powerful ways. Their intense radiation erodes nearby clouds. Their stellar winds push gas outward. When they eventually explode as supernovae, they send shock waves into space. These shock waves compress nearby gas and trigger the next generation of star formation. In this way, the birth and death of stars are linked in an ongoing cycle. Inside star-forming regions, we find structures called stellar nurseries. These nurseries glow with the light of young stars. Their gas is shaped into pillars, arcs, and cavities by the forces of radiation and wind. The famous pillars of creation in the Eagle Nebula are an example of such a region. Though we cannot see these nurseries with the naked eye, infrared and radio telescopes reveal their intricate forms. They are the factories of the galaxy, places where the raw material of the Milky Way turns into the starlight that fills our sky. The rate of star formation in the Milky Way has changed over time. Billions of years ago, the galaxy produced stars at a much higher rate. Today, the number is lower but still significant. Astronomers estimate that our galaxy forms about 7 new stars every year. These stars are distributed across the spiral arms, the places where gas density remains high enough for collapse. The Milky Way continues to evolve through this slow but steady process. Each new star adds energy, gravity, and chemical complexity to the galaxy. The chemistry of star-forming regions is also important. Inside these clouds lie molecules of carbon, oxygen, nitrogen, and other elements created in previous generations of stars. When a new star forms, these elements become part of its planets. They form the building blocks for water, air, and eventually life. Without earlier stars, the universe would contain only hydrogen and helium. Heavy elements exist because stars live and die. The birth of each new star is connected to the death of the stars that came before it. Some stars form in unusual environments. In the dense core of the galaxy, star formation follows different rules. Tidal forces near the central black hole stretch clouds and disrupt their motion. Yet young stars still appear in the region. Their formation suggests that under extreme conditions, new pathways emerge. These stars burn hot and fast. They shape the complex environment of the core. Their births and deaths contribute to the long-term evolution of the central region. Star birth is a slow process on human timescales. It unfolds over millions of years. Yet, in the life of the galaxy, it is a constant and essential function. Each star begins as a quiet region of darkness. Each star ends as a source of light and energy. The Milky Way is filled with these ongoing stories. When you see a bright star in the sky, you are seeing the final result of a long journey from cold gas to burning light. As we leave the nurseries of the galaxy, we step into the next stage of stellar evolution. The lives of stars are shaped by mass, temperature, and time. The next chapter follows these lives from their stable middle years to their dramatic ends. We explore how stars change, how they die, and how their deaths reshape the galaxy once again. Every star in the Milky Way follows a path shaped by one simple factor: its mass. Mass determines how brightly a star shines, how long it lives, and how it will die. A star begins its life as a newborn source of fusion, stable and balanced. Over time, it ages, changes, and eventually reaches an end that transforms both itself and the galaxy around it. To understand the Milky Way, we must understand these stellar lives and the roles they play in shaping the universe. Stars spend most of their existence in the main sequence phase. During this period, hydrogen atoms in the core fuse into helium. The energy produced by this fusion pushes outward, balancing the inward pull of gravity. This balance creates stability. For stars like our Sun, the main sequence lasts billions of years. During this time, the star shines with steady light, warming any planets that orbit it. Smaller stars, known as red dwarfs, burn even more slowly. They may last for hundreds of billions of years. Larger stars, however, burn through their fuel rapidly. Some last only a few million years before their time on the main sequence ends. As a star ages, its core changes. Hydrogen becomes helium, and the supply of hydrogen eventually decreases. When the core can no longer fuse hydrogen, gravity begins to take over again. The core contracts and heats up. Fusion moves outward into a shell around the core. The outer layers of the star expand. The star becomes larger, cooler, and brighter. For a star like the Sun, this marks the transition into the red giant phase. The red giant stage is dramatic. The star grows to many times its original size. If Earth still exists when the Sun reaches this phase, the planet will likely be scorched or consumed by the expanding star. Inside red giants, new types of fusion can occur. Helium in the core can fuse into carbon. If the star is massive enough, carbon can fuse into heavier elements. Each step requires higher temperatures and pressures. The star becomes a layered structure with multiple fusion zones. These zones create heavier and heavier elements, but each stage becomes shorter in duration. Eventually, the core can no longer sustain the required pressure for further fusion. What happens next depends on the mass of the star. For stars similar in mass to our Sun, the end comes quietly. The outer layers drift away into space, forming a glowing shell called a planetary nebula. The core that remains becomes a white dwarf. A white dwarf is a dense, hot object about the size of Earth, but with a mass similar to the Sun. It no longer produces fusion. It shines with leftover heat, slowly cooling over billions of years. White dwarfs are common in the Milky Way. They mark the final stage of most stars. More massive stars end their lives with far greater violence. When the core of a massive star cannot fuse new elements, it collapses under its own weight. This collapse is sudden. The outer layers of the star fall inward and then rebound in a powerful explosion known as a supernova. A supernova releases an enormous amount of energy. For a brief moment, a single star can outshine an entire galaxy. The shock wave from the explosion races outward, compressing nearby gas and triggering new rounds of star formation. The core left behind after a supernova depends again on mass. If the core is between certain limits, it becomes a neutron star. A neutron star is incredibly dense. A teaspoon of its material would weigh more than a mountain. Some neutron stars spin rapidly and emit beams of radiation. These objects are called pulsars. They create regular pulses of light and radio waves as they rotate. Pulsars provide valuable insight into extreme physics. They act as cosmic clocks, marking time with extraordinary precision. If the core of the massive star is heavy enough, the collapse does not stop with a neutron star. Instead, the core continues to compress until it forms a black hole. Black holes created by massive stars are much smaller than the supermassive black hole at the center of the galaxy, yet they are still powerful. Their gravity is so strong that nothing can escape once it passes the event horizon. These stellar mass black holes drift through the galaxy, often paired with companion stars. When matter from a companion star falls into the black hole, it emits high-energy radiation. This radiation reveals the presence of the black hole, even though the hole itself remains invisible. The death of stars plays a crucial role in the evolution of the Milky Way. Supernova explosions scatter heavy elements into space. Carbon, oxygen, nitrogen, and iron are all produced inside stars. These elements become part of future generations of stars and planets. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all created in stars that lived and died long before the sun was born. The galaxy becomes richer and more chemically complex with each cycle of stellar life and death. Star deaths also shape the structure of the galaxy. Shock waves from supernovae push gas across great distances. They clear cavities in the interstellar medium. They trigger new stars to form. Neutron stars and black holes add to the diversity of objects in the galaxy. White dwarfs quietly cool for eons, leaving behind the silent memory of stars that once shone brightly. Each outcome contributes to the Milky Way's ongoing story. Even though the life and death of stars unfold over millions or billions of years, we can observe different stages across the sky. Every point of light we see is a star in some phase of its journey. Some are young and vibrant. Some are aging and expanding. Some have already died, leaving behind faint remnants. The night sky is a record of these lives written in starlight. As we leave behind the life cycles of stars, our journey continues with the path of our own solar system. The next chapter explores how our solar system moves through the Milky Way, how this journey shapes conditions on Earth, and how the wider galaxy influences life in ways we seldom notice. Our solar system is not fixed in place. It travels through the Milky Way at great speed, carried along by the motion of the galactic disk. This journey is long and complex. It takes about 230 million years for the Sun to complete a single orbit around the center of the galaxy. In the time since life first appeared on Earth, our solar system has circled the Milky Way at least 17 times. Every moment of our planet's history has unfolded within this slow cosmic voyage. The path of the solar system is not a perfect circle. It is slightly elliptical and shaped by the gravity of the spiral arms, the central bar, and the halo of dark matter. As we orbit, we bob gently above and below the galactic plane. This up and down motion takes tens of millions of years. Some scientists think this vertical movement may play a role in patterns of climate on Earth by changing the amount of cosmic radiation that reaches the planet. Though the effect is still debated, it shows how our location in the galaxy can influence conditions on our world. As the Sun moves through the Milky Way, it encounters regions with different densities of gas and dust. Some regions are quiet and empty. Others are crowded with clouds of hydrogen, dark dust, and clusters of stars. When the solar system enters a denser region, the outer boundary of the heliosphere can shrink. The heliosphere is the protective bubble created by the solar wind. It shields the inner planets from some forms of cosmic radiation. A change in its size can alter the amount of high-energy particles that reach Earth. Over long time scales, this process may influence the climate and even the rate of mutations in living organisms. The solar system also moves relative to nearby stars. Over millions of years, different stars pass within a few light years of the Sun. These encounters are rare but significant. A close passing star can disturb the Oort cloud, the distant shell of icy bodies surrounding our solar system. Disturbed objects may fall inward and become comets. Some scientists propose that certain waves of comet activity in Earth's past could be linked to the movement of the solar system through the galaxy. Though these events are difficult to confirm, the idea highlights the subtle connections between galactic motion and activity in the inner solar system. The position of the solar system within the Orion Arm also matters. We are located in a relatively calm region between major spiral arms. This calmness protects us from frequent supernova explosions. In denser regions of the galaxy, supernovae occur more often. Their radiation can damage atmospheres and disrupt biological systems. Our distance from the core and from the major arms provides a stable environment for life. This stability may have been essential for the long evolutionary journey that eventually produced complex organisms, including humans. As we travel through the Milky Way, the sky above Earth slowly changes. Constellations shift. Bright stars move to new positions. Over tens of thousands of years, the night sky becomes unrecognizable compared to what we see today. The motion of the solar system also changes the direction of starlight that reaches Earth. This effect, known as proper motion, is slow but measurable. Astronomers use it to trace the paths of nearby stars and reconstruct the recent history of our local region within the galaxy. Our solar system's orbit is influenced by the total mass of the Milky Way. This includes not only stars and gas, but also dark matter. Dark matter creates a gravitational field that adds stability to the orbit. Without it, the Sun's movement would not match the observed pattern. The presence of dark matter ensures that the solar system remains bound to the galaxy, held in place by an invisible structure that reaches far beyond the visible disk. Even though our journey through the Milky Way takes hundreds of millions of years, we can understand it through careful measurement. Astronomers use the motion of the Sun relative to nearby stars to calculate our speed. The solar system travels at about 500,000 miles per hour around the galactic center. Despite this high speed, we do not feel the motion. Everything around us moves together, forming a stable local environment even as we travel across vast cosmic distances. The path of the solar system has shaped Earth's past and will shape its future. Eventually, we will come closer to other regions of the galaxy. In about 150 million years, we may drift toward a new part of the Orion Arm. In a few billion years, the Milky Way will merge with the Andromeda Galaxy, altering the entire structure of the sky. Through it all, the solar system will continue its long orbit, carrying Earth through an ever-changing environment shaped by the forces that govern the galaxy. When we look up at the night sky, we see stars that appear fixed in place, yet they are all moving. The galaxy is in constant motion. Every star follows its own path. Every cloud drifts. Every planet circles its sun while the sun circles the galaxy. This motion reminds us that nothing in the universe is still. Everything participates in the endless flow of time and gravity. As we leave the solar system's journey and move outward once again, the next chapter explores one of the most mysterious structures of the Milky Way, the vast and silent halo that surrounds the galaxy and holds some of its oldest secrets. Surrounding the bright disk of the Milky Way is a vast and quiet realm known as the galactic halo. Unlike the crowded spiral arms or the glowing core, the halo is a place of openness and ancient light. It extends far beyond the visible edges of the galaxy. Most of its mass is invisible. Most of its contents are overlooked by the naked eye. Yet, the halo plays a central role in shaping the Milky Way and anchoring its structure across cosmic time. The halo can be divided into two main parts: the stellar halo and the dark matter halo. The stellar halo contains stars that drift in long and distant orbits. These stars are old. Many formed more than 10 billion years ago, long before the disk of the galaxy reached its modern shape. They shine faintly and are scattered across a huge volume of space. Their motions are erratic compared to the organized rotation of stars in the disk. Some plunge through the galactic plane in steep arcs. Others move in slow and extended loops. Their paths reveal that they were not born in the disk, but came from ancient mergers with smaller galaxies. One of the most striking features of the stellar halo is the presence of star streams. These are long trails of stars that stretch across thousands of light years. Star streams form when the Milky Way absorbs smaller galaxies. As a dwarf galaxy is pulled apart by gravity, its stars spread out along its orbit. Over time, the stream becomes a faint ribbon of light. Astronomers have identified many such streams. Each one is a remnant of a past collision. Together, they provide a record of how the Milky Way grew through the slow process of galactic cannibalism. Globular clusters also inhabit the halo. These clusters are dense spheres of stars held together by gravity. Some contain hundreds of thousands of stars packed into a region only a few dozen light years wide. The stars in globular clusters are among the oldest in the galaxy. Their chemical compositions reveal that they formed early in the Milky Way's history, when heavy elements were rare. These clusters orbit the galaxy in wide loops that carry them far above and below the disk. They act as time capsules, preserving the early conditions of the universe. Far beyond the stellar halo lies the dark matter halo. Dark matter is invisible, yet its presence is undeniable. It does not emit light. It does not absorb light, but it exerts gravity. Without dark matter, the Milky Way would not hold together. The stars in the outer regions of the disk move faster than expected if only visible matter were present. This extra speed reveals an unseen mass. The dark matter halo extends hundreds of thousands of light years from the center of the galaxy. It forms a massive and diffuse envelope that surrounds the entire system. The nature of dark matter remains one of the greatest mysteries in science. We know it is not made of ordinary atoms. We know it interacts weakly with light and with normal matter. We also know it makes up most of the mass of the galaxy. Dark matter shapes the orbits of stars, the behavior of gas clouds, and the formation of spiral arms. It influences the growth of galaxies across the universe. Though we cannot see it directly, the Milky Way's structure would collapse without it. The halo of dark matter is the invisible foundation on which the galaxy is built. The halo also contains gas, though it is extremely thin compared to the gas in the disk. This gas is hot, with temperatures reaching millions of degrees. It forms a cloud known as the circumgalactic medium. This medium acts as a reservoir of material that can flow into the disk and form future stars. It also receives gas pushed outward by supernova explosions and by past activity near the galactic core. The circumgalactic medium connects the Milky Way to the larger cosmic environment. It is part of a continuous exchange between galaxies and intergalactic space. The halo is not empty. It contains dwarf galaxies that orbit the Milky Way. These small galaxies are fragile and easily influenced by gravity. Some are being torn apart as we observe them. Others remain intact, moving through long orbits that carry them high above the disk. The most famous examples are the Large Magellanic Cloud and the Small Magellanic Cloud. These galaxies are visible from the southern hemisphere as bright patches of light. Their interactions with the Milky Way create long trails of gas and influence star formation in both systems. Because the halo is vast and faint, it is difficult to study with direct observation. Astronomers rely on careful measurements of stellar motion, chemical composition, and gravitational effects. Large sky surveys and space telescopes have transformed our understanding of the halo in recent decades. They reveal a structure that is layered, complex, and full of history. The halo is not a simple sphere. It has streams, substructures, and remnants of long-forgotten galaxies. It is a fossil record written in stars. The halo also influences life on Earth in subtle ways. Its gravitational pull helps shape the orbit of the solar system. Its dark matter sets the framework for the distribution of stars in the disk. Even the formation of the sun depended on the larger environment of the halo. Without dark matter, the Milky Way would have formed differently, and the conditions for life might never have emerged. The halo may be quiet, but it is essential. When we look at the Milky Way from a dark location on Earth, we see a bright band of stars stretched across the sky. What we cannot see is the immense structure that surrounds it. The halo carries the memory of the galaxy's past and the foundation of its present. It connects the Milky Way to the larger universe and anchors its form against the pull of time. As we move from the mysterious halo to one of the greatest cosmic enigmas, the next chapter explores dark matter in more detail. We dive deeper into its nature, its role, and the unanswered questions that make it one of the most profound mysteries in modern astronomy. Dark matter is one of the most puzzling and important ingredients in the Milky Way. It does not shine. It does not glow. It does not absorb or reflect light. Yet, it makes up most of the mass of our galaxy. Without dark matter, the Milky Way would not hold together. The stars would not follow their observed orbits. The spiral arms would not maintain their graceful shape. The galaxy as we know it would not exist. Dark matter is invisible, but its influence is everywhere. Astronomers first suspected dark matter when they measured the rotation of galaxies. In the early 20th century, scientists expected that stars farther from the center would orbit more slowly than stars close to the center. This expectation came from the rules of gravity. If most mass was near the center, outer stars should drift at gentle speeds. But when astronomers measured the rotation of galaxies, including the Milky Way, they found something surprising. Outer stars were moving just as fast as stars near the center. This behavior did not match the visible mass. Something unseen had to be providing extra gravity. The idea of dark matter took shape as scientists reviewed the evidence. They studied star clusters orbiting galaxies. They measured gas clouds far from the galactic disk. They examined the motion of satellite galaxies. Every measurement pointed to the same conclusion. Galaxies contain far more mass than what we can detect with light. This missing mass was named dark matter. The Milky Way is surrounded by a massive dark matter halo that extends far beyond the visible stars. This halo adds weight to the galaxy and holds it together. Dark matter does not interact with normal matter in the way we are familiar with. It does not collide with gas or dust. It does not form atoms. It does not burn. It passes through normal matter without friction, yet it exerts gravity. This gravity shapes the motion of stars, the structure of spiral arms, and the behavior of gas clouds. It also influences the formation of galaxies across the universe. In the early universe, dark matter created gravitational wells that pulled in normal matter. These wells formed the seeds of galaxies. Without dark matter, the Milky Way would not have formed in the way it did. There are several ideas about what dark matter might be. Some scientists propose that it is made of exotic particles that interact only weakly with normal matter. These particles would be difficult to detect, but not impossible. Experiments deep underground and in space attempt to capture rare interactions between dark matter particles and normal particles. So far, no direct detection has been confirmed. Other theories suggest that dark matter could be made of unseen compact objects, but observations do not support this. The most widely accepted view is that dark matter is a new type of particle, different from anything found in the periodic table. One of the strongest pieces of evidence for dark matter comes from galaxy collisions. When two galaxies crash together, their stars pass through each other with little interaction. Gas clouds, however, collide and slow down. In some galaxy collisions, astronomers observed that the majority of mass continued moving with the stars, not with the slowed gas. This mass did not emit light. It acted like an invisible structure that moved through the collision unaffected. This behavior matches what we expect from dark matter, which interacts through gravity but not through collisions. The dark matter halo of the Milky Way shapes the galaxy in many ways. It determines the speed at which stars orbit. It keeps the spiral arms stable. It influences the motion of satellite galaxies. It may also affect the rate of star formation. As gas moves through the disk, gravity from the halo helps hold it in place. This stability allows gas to cool and collapse into new stars. Without the halo, the disk might be too unstable for steady star formation. The halo also affects the path of our solar system. As we orbit the center of the Milky Way, we move through the gravitational field created by dark matter. This field is smooth and uniform on large scales. It provides the extra mass needed to keep our orbit steady. Though dark matter is invisible, its presence is felt in every movement of the solar system across the galaxy. Dark matter remains one of the most active areas of research in modern astrophysics. New telescopes and instruments continue to refine our understanding of how it behaves. Large surveys of the sky reveal the distribution of dark matter through its gravitational effects. Computer simulations show how dark matter shaped the early universe and guided the formation of galaxies. Each advance brings us closer to understanding this mysterious substance. Yet the true nature of dark matter remains unknown. The mystery of dark matter reminds us that the universe is larger and stranger than our daily experience. We are surrounded by forces we cannot see. We live inside a galaxy whose structure depends on matter that does not shine. The fact that dark matter shapes the Milky Way without revealing itself makes it one of the greatest scientific puzzles of our time. As we leave the realm of the invisible and return to the visible worlds around distant stars, the next chapter explores exoplanets. We shift our focus from the dark skeleton of the galaxy to the diverse and surprising planets orbiting stars across the Milky Way. Across the Milky Way, billions of planets orbit distant stars. These planets are called exoplanets, and they come in a remarkable variety of sizes, temperatures, and compositions. For most of human history, we believed that our solar system might be unique. We wondered if other worlds existed beyond our reach. That changed in the early years of the 21st century when new telescopes revealed the first clear evidence of planets orbiting other stars. Today, we know that planets are common. Almost every star in the galaxy likely has at least one. The discovery of exoplanets began with careful observation. Scientists examined the light from distant stars and noticed tiny dips in brightness. These dips occurred when a planet passed in front of the star. This transit method allowed astronomers to detect worlds hundreds of light years away. The Kepler Space Telescope expanded this work by observing one small region of the sky for years. Kepler revealed thousands of planets and showed that Earth-sized worlds are not rare. Many stars host systems of multiple planets arranged in complex orbits. Exoplanets differ from the planets in our solar system in dramatic ways. Some orbit extremely close to their stars. These planets are called hot Jupiters. They are massive gas giants that complete an orbit in a few days. Their temperatures are intense. Their atmospheres boil and flow like rivers of heated gas. Other exoplanets are far from their stars, drifting through cold and dim environments. Some have orbits so elliptical that they move from scorching heat to freezing cold in a single year. There are rocky exoplanets similar to Earth and Mars. There are super-Earths, which are larger and heavier than our planet but still solid. Some may have thick atmospheres. Some may have oceans that cover their entire surface. There are mini Neptunes, small gas-rich planets with deep atmospheres and no solid surface. There are water worlds, planets that may hold oceans hundreds of miles deep. Each type expands our understanding of what a planet can be. One of the most important goals in exoplanet research is the search for habitable worlds. A habitable world is one where temperatures allow liquid water to exist on the surface. This depends on the distance from the star. If a planet orbits too close, its water will boil. If it orbits too far, its water will freeze. The habitable zone is the region where liquid water can remain stable. Many exoplanets have been found in this zone. Some orbit stars smaller and cooler than the Sun. These stars, called red dwarfs, are common in the Milky Way. Their planets may be abundant, but red dwarfs can produce strong flares that may strip atmospheres from nearby worlds. The atmosphere of an exoplanet is a key factor in its potential to support life. Scientists use a method called spectroscopy to study atmospheres. When a planet passes in front of its star, some of the starlight passes through the atmosphere. Different molecules absorb light at specific wavelengths. By studying these patterns, astronomers can identify the gases in the atmosphere. Water vapor, methane, oxygen, and carbon dioxide are among the chemicals that could indicate biological activity. Though we have not yet found clear evidence of life, advances in spectroscopy are bringing us closer to detecting possible biosignatures. Some exoplanets orbit in tightly packed systems where multiple worlds circle their star at close distances. The TRAPPIST system is a well-known example. It contains 7 Earth-sized planets, 3 of which lie in the habitable zone. The system is compact. All 7 planets orbit closer to their star than Mercury orbits the Sun. Yet each planet may still have conditions that support liquid water. Systems like TRAPPIST challenge our assumptions about stability and habitability. The diversity of exoplanets suggests that the Milky Way is rich with environments that differ from anything in our solar system. Gas giants may orbit close to red dwarfs. Rocky planets may orbit blue giant stars. Planets may exist in binary systems with 2 suns. Some planets may wander freely without orbiting any star at all. These rogue planets drift through the galaxy in darkness. They may have internal heat from radioactive decay or from compression. Though they receive no starlight, they could hold underground oceans. The discovery of exoplanets has changed our perspective on the universe. We now see the Milky Way as a place filled with planetary systems. Each star may host its own collection of worlds. Some may resemble Earth. Others may be entirely alien. The number of planets in the galaxy likely exceeds the number of stars. This means that the Milky Way holds billions of potential environments where new forms of chemistry and new possibilities for life might arise. Though the study of exoplanets has grown rapidly, we have explored only a small fraction of the galaxy. Most exoplanets discovered so far are close to Earth in cosmic terms. They lie within a few thousand light years. Beyond that distance, our tools become less sensitive. Yet the Milky Way spans 100,000 light years. The majority of planets remain unknown. Future telescopes will expand our reach and reveal worlds we have not yet imagined. As we continue this journey through the galaxy, the next step brings us deeper into one of humanity's oldest questions, the question of life beyond Earth. The next chapter explores how scientists search for life across the Milky Way, how we interpret signs of biology, and what discoveries might mean for our understanding of our place in the universe. The search for life in the Milky Way is one of the deepest scientific efforts of our time. It unites astronomy, chemistry, biology, and planetary science. It reaches across thousands of light years and across billions of years of cosmic history. At the core of this search is a simple idea. Life may not be unique to Earth. The conditions that allowed life to form here may exist on other worlds. If the Milky Way holds billions of planets, then some of those planets may hold environments suitable for biology. The challenge is to find the signs that life leaves behind. The first step in the search is to understand the requirements for life as we know it. Life on Earth depends on liquid water, stable temperatures, and a supply of chemical energy. These conditions can exist on rocky planets in the habitable zone of their stars. They can also exist in subsurface oceans beneath layers of ice. They may even exist in environments warmed by tidal forces rather than sunlight. Because we only know one example of life, we use the Earth-based model as a starting point. We search for worlds with the right temperature, the right chemistry, and the right stability. The next step is to look for biosignatures. A biosignature is a chemical or physical signal that life may produce. Earth offers many examples. Our atmosphere contains oxygen produced by photosynthesis. It also holds methane produced by biological processes. If an astronomer on a distant world observed Earth they would detect a mix of gases that are difficult to explain without life. When we observe exoplanets, we search for similar patterns. Using spectroscopy, we examine the light that passes through a planet's atmosphere. We analyze how molecules absorb that light. Each molecule leaves a distinct fingerprint. If we detect a combination of gases that suggests an active and stable environment, we may have found a candidate for life. Another approach is the search for technosignatures. These are signals that may be produced by advanced civilizations. The most famous technosignature is radio communication. For decades, scientists have listened for narrow-band radio signals that do not occur naturally. This work is known as SETI, the search for extraterrestrial intelligence. Though no confirmed signals have been found, SETI continues to refine its tools. Modern instruments can scan millions of frequencies at once. They can survey entire regions of the sky far more quickly than earlier systems. As technology improves, the search becomes broader and more sensitive. Life, however, may not reveal itself through technology. Most life on Earth is not technological. Thousands of species have existed for millions of years without producing radio signals or visible structures. For this reason, the search includes planets that may hold only microbial life. Microbial life could alter the chemistry of oceans, rocks, or atmospheres. These changes could be detected from afar. Some of the best targets for microbial life are planets orbiting red dwarf stars. Red dwarfs are common and often host rocky planets. If those planets can retain their atmospheres despite stellar flares, they may hold stable environments for long periods. The Milky Way contains many environments where life could exist away from starlight. One example is subsurface oceans. In our own solar system, moons like Europa and Enceladus have oceans beneath layers of ice. These oceans may be warmed by tidal forces that stretch and compress the moon as it orbits its planet. Hydrothermal vents on the ocean floor could provide energy in the form of chemical gradients. Similar environments may exist on distant exoplanets or on rogue planets drifting through space. Even without sunlight, life could emerge in dark oceans powered by internal heat. The search for life also includes the study of atmospheric stability. An atmosphere that remains balanced over millions of years may suggest long-term processes. On Earth, life maintains a stable balance of gases. Oxygen, carbon dioxide, and methane remain within ranges shaped by biological activity. If we find a planet with a stable and active atmosphere, we ask whether geological processes alone can explain it. If not, life becomes a possibility. Some scientists explore the idea that life may use chemistry different from Earth-based biology. This is known as the hypothesis of alternative biochemistry. Instead of water, life could use liquid methane. Instead of carbon, it could use silicon. These ideas expand the range of possible habitats. However, detecting such life from afar is more challenging. We do not yet know what signs non-carbon-based life would leave. For now, the search focuses on environments similar to Earth while keeping an open mind to other possibilities. As we study more exoplanets, we begin to see patterns. Some planets have thick atmospheres rich in carbon dioxide. Others show hints of water vapor. A few show surprising features that raise questions about their chemistry. None have yet shown a definitive biosignature. But every year, the data grows. New telescopes, such as the James Webb Space Telescope, allow us to study exoplanet atmospheres with greater precision. In the coming decades, larger observatories may directly image distant Earth-like planets. they may detect oceans, clouds, or surface features. The search for life is not only scientific, it is also philosophical. If we find life elsewhere in the Milky Way, even simple life, it would change our understanding of our place in the universe. It would show that life can emerge more than once. It would suggest that the universe may be full of living systems. On the other hand, if the search continues for centuries without success, it may suggest that Earth is rare or even unique. Both possibilities carry profound meaning. For now, the search continues with patience and curiosity. We listen for signals. We study atmospheres. We explore the diversity of planets across the galaxy. The Milky Way is vast, and our investigations have only begun. Life may be common or rare. It may be near or far. It may reveal itself soon or remain hidden for generations. As we leave the search for life and continue our journey, the next chapter explores the idea of galactic weather. We turn our attention to the forces that shape the large-scale environment of the Milky Way, from magnetic fields to cosmic rays and the great flows of gas that move through the galactic disk. When we think of weather, we picture clouds, wind, rain, and storms on Earth. But the Milky Way has its own form of weather. It is not weather of air or water. It is weather made of gas, dust, radiation, and magnetic fields that move across thousands of light years. This galactic weather shapes the environment of the entire galaxy. It influences star formation, the flow of matter, and the conditions that surround planetary systems like our own. The most basic component of galactic weather is gas. The Milky Way contains vast clouds of hydrogen that drift through the disk. Some clouds are cold and calm. Others are hot and turbulent. These clouds move slowly under the influence of gravity. When a supernova explodes, it sends a shock wave through space. This wave travels outward and compresses nearby gas. It can trigger new star formation or clear out cavities in the interstellar medium. Over millions of years, these shock waves create a patchwork of dense regions and empty spaces. Magnetic fields also shape galactic weather. The Milky Way has a weak but widespread magnetic field that threads through the disk. This field aligns charged particles and influences how gas flows. It shapes the structure of molecular clouds and guides the movement of cosmic rays. Though the magnetic field is too weak to affect planets directly, it plays a major role in the behavior of interstellar matter. Observations using polarized light reveal long strands of dust that follow the magnetic field lines. These strands look like fibers woven across the galaxy. Cosmic rays are another major force in the weather of the Milky Way. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. Many come from supernova explosions. Others come from the regions around black holes. When cosmic rays move through the galaxy, they collide with gas molecules and create secondary particles. These interactions heat the interstellar medium and influence chemical reactions. Cosmic rays also reach Earth. The atmosphere protects us from most of them. Yet they still play a small role in the rate of mutations in living organisms. Cosmic rays are part of the invisible connection between galactic events and life on our planet. Galactic weather also includes large-scale flows of gas driven by long-term processes. One example is the outflow of material from the galactic center. In the past, the region around Sagittarius A was more active. It released energy that pushed gas outward. Today, we can see the evidence of this activity in the form of giant structures called the Fermi bubbles. These bubbles contain high-energy particles and extend above and below the plane of the Milky Way. They are like scars from a powerful storm that swept through the galaxy millions of years ago. Another example of large-scale flow is the movement of gas along the spiral arms. As the arms rotate, they create pressure differences that push gas into new regions. This motion acts like a conveyor belt that moves material across the disk. Some gas flows inward toward the center. Some flows outward toward the edges of the galaxy. These flows regulate star formation by delivering fresh material to some regions and removing it from others. Over billions of years, this circulation helps shape the distribution of stars in the Milky Way. Dust also participates in galactic weather. Dust grains are tiny solid particles made of carbon, silicon, and other elements. They form in the atmospheres of dying stars and in the debris of supernovae. Dust drifts through the galaxy, mixing with gas. It blocks visible light and creates dark lanes in the spiral arms. Dust can absorb energy and re-emit it as infrared radiation. This process helps regulate the temperature of the interstellar medium. Dust is essential for the formation of molecular clouds because it provides surfaces where molecules can form. Without dust, star formation would be far less efficient. The interactions between gas, dust, radiation, and magnetic fields create complex patterns. These patterns evolve slowly. A region of dense gas may collapse into a star-forming cloud. A supernova may then explode and clear the region. Over millions of years, the cycle repeats. The galaxy breathes through these processes. It expands and contracts. It heats and cools. It creates and destroys. Galactic weather is the heartbeat of the Milky Way. Though these forces are powerful on large scales, they can also influence the local environments of planetary systems. When a supernova explodes near a solar system, it may send a wave of cosmic rays that can alter atmospheric chemistry over long timescales. The solar system passes through regions with different levels of dust and gas. These changes can affect the size of the heliosphere and the flow of interstellar particles. In this way, galactic weather touches every world, even Earth. Understanding galactic weather requires many types of observations. Radio telescopes map hydrogen gas. Infrared observatories reveal dust structures. X-ray instruments detect high-energy regions. Magnetic fields are studied through polarized light. Together, these tools allow astronomers to build a picture of the Milky Way as a dynamic and ever-changing system. Galactic weather is not as fast as a storm on Earth, but it is just as real. It moves over millions of years instead of minutes. Yet its effects shape the history of the galaxy. As we move forward in our journey, we now step into the history of the Milky Way itself. The next chapter explores the ancient collisions and mergers that built the galaxy, revealing how the Milky Way grew through encounters with other star systems. The Milky Way did not form as a single structure. It grew over billions of years through collisions and mergers with smaller galaxies. These ancient encounters shaped the size, the shape, and the internal structure of the galaxy we see today. Every collision left behind traces that still drift through the halo and the disk. To understand the Milky Way as it exists now, we must look back at the slow and dramatic interactions that built it. In the early universe, galaxies were small and irregular. Gravity brought these young systems together. When two galaxies approached each other, their stars passed through without colliding, because stars are spaced far apart. But their gravity pulled on each system. Tidal forces stretched the galaxies into long trails of stars. Gas clouds collided and compressed. New stars burst into existence. Over time, the smaller galaxy became disrupted and absorbed into the larger one. This process is known as galactic cannibalism. It is one of the main ways large galaxies grow. The Milky Way has absorbed many small galaxies. Some of these mergers happened so long ago that their remnants are now indistinguishable from the rest of the disk. Others left behind structures that we can still observe. One of the most famous examples is the Sagittarius dwarf galaxy. This small galaxy is being torn apart by the Milky Way. Its stars form long streams that wrap around the disk. These streams act like cosmic fossils. They show how material moves when a galaxy is absorbed and how the halo gains new stars. Another major event in the history of the Milky Way was the merger with a system known as Gaia Enceladus. This collision happened about 10 billion years ago. It was large enough to reshape the galaxy. The stars from Gaia Enceladus now form part of the stellar halo. Their orbits are more chaotic than the orbits of stars born in the disk. Their chemical composition is different, showing lower levels of heavy elements. This indicates that Gaia Enceladus was a smaller and less chemically evolved galaxy. Its merger triggered star formation and helped create the thick disk of the Milky Way. The halo contains many such remnants. Star streams crisscross the sky. Globular clusters move along paths that hint at ancient origins. Some clusters may be the cores of small galaxies that were stripped of their outer stars. By mapping the motion of halo stars, astronomers reconstruct the past collisions. Each collision added mass to the Milky Way. Each collision changed the shape of the disk. Each collision helped build the galaxy into the system we inhabit today. Galactic collisions are slow. They unfold over billions of years. When two galaxies approach each other, they do not crash in the way two solid objects do. Instead, they pass through and around each other multiple times. Their shapes distort. Their gas collects in new regions. Their stars follow new paths. After many passes, they merge into a single system. The process creates waves of star formation and new structures within the disk. The Milky Way continues to interact with its surroundings. The large Magellanic Cloud and the small Magellanic Cloud orbit the galaxy and influence the motion of gas within the halo. These galaxies may one day merge with the Milky Way. Their motion also pulls on the dark matter halo, creating subtle shifts in the gravitational field. These shifts can affect the orbits of stars across the galaxy. Even now, the Milky Way is not a static structure. It is a dynamic system influenced by both internal and external forces. The most dramatic future event will be the collision between the Milky Way and the Andromeda Galaxy. Andromeda is the closest large galaxy to us. It is moving toward the Milky Way at great speed. In about 4 billion years, the two galaxies will begin to merge. The sky above Earth will change as Andromeda grows brighter. Over millions of years, the two systems will pass through each other and eventually form a new, larger galaxy. This galaxy is sometimes called Milk-Dromeda. The Sun will likely survive the collision, but its orbit will change as the gravitational environment shifts. Planetary systems like ours may be thrown into new regions of space. Though galactic collisions sound violent, they rarely destroy stars directly. Space between stars is wide. The danger comes from gravitational disturbances that alter orbits, and from the increased star formation that can lead to more supernovae. Yet these processes also create beauty. New stars form. New planets emerge. The structure of the galaxy renews itself. The story of ancient collisions is a story of change. The Milky Way grew not by remaining isolated, but by interacting with the universe around it. Every star stream, every globular cluster, and every ripple in the halo is evidence of these encounters. By piecing together the remains, astronomers build a timeline of galactic evolution. They see how the Milky Way expanded from a small, early galaxy into the massive spiral we call home today. As we leave the era of ancient mergers and look toward the future, the next chapter explores what lies ahead for the Milky Way. We examine how the galaxy will evolve, how stars will fade, and how the slow rhythm of cosmic time will shape the long-term destiny of our galactic home. The Milky Way is not a finished structure. It is still changing, still evolving, and still shaped by forces that move across billions of years. To understand its future, we must slow our sense of time to the pace of the galaxy. Stars will fade. Gas will flow. The structure of the spiral arms will shift. Entire regions will transform. The story of the Milky Way continues long after the present moment and stretches into a future where the galaxy becomes a different place from the one we know today. For now, the Milky Way remains active in forming stars. Gas in the spiral arms continues to collapse into new suns. But the supply of gas is not endless. Over billions of years, star formation will slow as gas becomes locked inside long-lived stars or blown into the halo by supernova explosions. The brightest and hottest stars will form early and die quickly. The smaller and cooler stars will last for trillions of years. The overall brightness of the galaxy will gradually fade as the balance shifts toward faint and long-lived stars. Our sun also has a future that ties into the larger fate of the galaxy. In about 5 billion years, the sun will exhaust its core hydrogen. It will expand into a red giant and then shrink into a white dwarf. By that time, Earth will no longer be habitable. The planet may be consumed by the expanding sun or reduced to a scorched remnant. Yet the galaxy will continue. Other stars will form. Other planets will emerge. Other systems will experience their own cycles of creation and destruction. The most dramatic event in the future of the Milky Way is the collision with the Andromeda galaxy. Andromeda is moving toward us at high speed. The two galaxies will meet in about 4 billion years. The first encounter will stretch and distort both galaxies. Tidal forces will pull long streams of stars into space. Gas clouds will collide and create powerful waves of star formation. The night sky on Earth, if Earth still exists, will show the glowing form of Andromeda growing larger with each passing million years. The merger itself will unfold over a long period. The galaxies will pass through each other, separate, and then fall back together. The final union will occur after several passes. The result will not be a spiral galaxy. Instead, the Milky Way and Andromeda will form a large elliptical galaxy, sometimes called Milkdromeda. The spiral arms will fade. The disk will thicken. Star formation will slow as gas becomes scattered and heated. The new galaxy will be larger, rounder, and more diffuse. During the merger, the stars of both galaxies will mix, but direct collisions between stars will remain rare. The danger will come from the shifting gravitational environment. Planetary systems may be pushed into new orbits. Some may be thrown into intergalactic space. Others may move closer to the center of the new galaxy. The supermassive black holes at the center of the Milky Way and Andromeda will spiral toward each other and eventually merge. This event will release a burst of gravitational waves that will ripple through space. After the merger, the new galaxy will settle into a long period of slow evolution. Over trillions of years, star formation will decline. The bright young stars will fade. red dwarfs will dominate. White dwarfs will cool into black dwarf remnants. The galaxy will become a quieter place. The interstellar medium will thin. The large-scale structure will stabilize. Over extremely long timescales, the Milky Way as we know it will fade into a system of old stars drifting in dim light. Throughout this distant future, dark matter will continue to hold the galaxy together. Its gravitational field will remain, shaping the orbits of the remaining stars. But even dark matter may change on scales of time far beyond our current understanding. The universe itself will continue to expand. Distant galaxies will move farther away as cosmic expansion accelerates. One day, only the remnants of the merged Milky Way and Andromeda will remain visible to any future observers within it. Though this future may seem quiet and cold, it reflects the natural cycle of galaxies. They are born in clouds of gas. They grow through collisions. They shine brightly for billions of years. Then they slowly fade. The Milky Way is currently in a mature and active stage of its life. It has formed countless stars. It has nurtured planets. It has supported the development of life. The future will carry these processes forward in new forms, shaped by the slow and graceful flow of cosmic time. When we consider the future of the Milky Way, we are reminded that galaxies are living systems. They change. They evolve. They respond to the forces around them. Our moment in the galaxy is a brief one, but it is part of a much larger story. The stars that shine above us today will not always shine. The sky will not always look the way it does now. But the galaxy will endure in new forms, shaped by gravity, time, and the quiet persistence of cosmic evolution. As we step from the future into the present moment once again, the final chapter explores what it means for humanity to live in the Milky Way. We reflect on our place in this galaxy, our connection to its stars, and the meaning of belonging to a system that has shaped us from the beginning. We end our journey through the Milky Way by returning to the question that has guided us from the beginning. What is our place in this vast and ancient galaxy? The Milky Way is immense. It spans 100,000 light years. It holds hundreds of billions of stars. It contains streams of matter, clouds of gas, and fields of invisible dark matter. It has lived through collisions, storms, and cycles of birth and death. And yet, within this enormous structure, there exists a small star, a small planet, and a species that has learned to ask where it belongs. Humans have always been shaped by the sky. Long before science emerged, people felt a connection to the stars. They used them to navigate across oceans and deserts. They wove them into stories about creation and identity. As our tools improved, we discovered that the stars are not just lights in the night. They are suns. They are distant worlds. They are milestones in a larger structure that we now call the Milky Way. With each discovery, our sense of scale expanded. We learned that our solar system is one of billions. We learned that our planet is one of countless possibilities. We learned that we live inside a galaxy that has shaped everything we know. The atoms in our bodies come from the Milky Way. Hydrogen from the first moments of the universe fills our cells. Carbon, oxygen, and nitrogen were formed inside stars that lived and died long before the sun existed. Iron was forged in the hearts of massive stars and scattered through space by exploding supernovae. When the sun formed, it collected this material. Earth formed from the same dust. Life emerged from the chemistry of these ancient elements. We are made of the galaxy. Our physical existence is a record of its long and complex history. Our position in the Milky Way also played a role in the development of life. We orbit at a calm distance from the galactic center. We lie between major spiral arms in a region with moderate radiation and fewer catastrophic events. This stability gave evolution the time it needed. It allowed life to progress through countless generations. It allowed complexity to grow. Even the shape of our orbit, the motion of our star, and the presence of dark matter influenced the environment that made life possible. The galaxy did not shape us directly, but it shaped the conditions in which we could arise. Now we enter a new stage in our relationship with the Milky Way. We have begun to measure its structure. We have mapped its stars. We have studied its history through the motion of ancient clusters. We have detected planets around distant suns. We have learned to listen for signals that might come from other civilizations. Though we remain a young species compared to the age of the galaxy, we have already taken steps toward understanding our cosmic home. The search for life beyond Earth also reshapes our sense of place. If life exists elsewhere in the Milky Way, then we are part of a larger community of worlds. If life is rare, then we carry a responsibility to preserve and understand the unique environment that allowed us to exist. Either possibility deepens our connection to the galaxy. The Milky Way is not just the background for human life. It is the environment that made life possible and the frontier that will shape our future. As we look ahead, humanity may one day venture beyond the solar system. We may send probes to distant stars. We may explore exoplanets with robotic instruments. Far in the future, we may build habitats that drift through interstellar space. These ideas feel distant, yet they reflect the same curiosity that has driven exploration throughout human history. The Milky Way is vast, but it is not unreachable. It invites us to look outward and imagine what lies beyond the next horizon. At the same time, the galaxy reminds us of our limitations. The distances between stars are enormous. The timescales of cosmic evolution are long beyond human lifetimes. Many mysteries of the Milky Way will require generations of research. But our progress shows that understanding grows with time. Each discovery builds on those that came before. Each new tool expands our vision. The galaxy reveals itself slowly, with patience and persistence. In the end, our place in the Milky Way is both small and significant. We are small in size, a single species on a single planet orbiting a single star. But we are significant in awareness. We can look up, we can ask questions, and we can seek answers. We can trace our origins to the stars. We can see the path of our solar system through the galaxy. We can imagine the future of the Milky Way long after our own time has passed. To belong to the Milky Way is to be part of a story that began billions of years before us and will continue billions of years after us. It is a story of gravity and gas, of stars and dust, of creation and transformation. It is a story written in light and matter and time. And within that story, humanity has found a place, not at the center, but as one small voice speaking into the vastness. As we conclude this journey, we return to the night sky. The band of the Milky Way arches above us, faint yet steady. It carries the memory of ancient stars and the promise of future worlds. It reminds us that we live inside a galaxy full of secrets, and that the search to understand those secrets is part of what makes us human. We have traveled from the glowing center of the galaxy to the quiet edges of the halo. We have explored the birth of stars, the death of suns, the drift of planets, and the silent framework of dark matter. Along the way, we discovered that the Milky Way is not just a structure of gas and light. It is a living system held together by gravity and shaped by time. The galaxy will continue to evolve. Stars will form. Stars will fade. Planets will circle their suns. Collisions will reshape the sky. New mysteries will emerge. Our place within this vast system may be small, but our ability to understand it is extraordinary. Through science, curiosity, and imagination, we reach across the darkness and uncover the forces that shape our home in the universe. As you step away from this final chapter, look up whenever you can. See the thin band of starlight that arcs across the night. Know that you are looking into the structure that created you. Know that you belong to a galaxy filled with history and possibility. And know that the secrets of the Milky Way will continue to unfold, waiting for the next curious mind to explore them. Good night.